Today we're going to explore a fascinating paradox that sits at the intersection of thermodynamics, phase transitions, and culinary art. This is the paella paradox. Imagine a traditional paella pan filled with rice and liquid. Classical equilibrium thermodynamics makes a clear prediction about what should happen. We have a shallow pan with rice grains submerged in water. Heat is applied from below. What does thermodynamics predict? Classical equilibrium thermodynamics makes a straightforward prediction. When a liquid is heated in a container, thermal equilibrium should establish a uniform temperature throughout the liquid phase. The prediction is clear. All the rice, whether at the bottom or near the surface, should cook at essentially the same temperature. Why? Because water is an excellent conductor of heat through convection. We expect the temperature at the bottom to be approximately equal to the temperature at the top, both around 100 degrees Celsius at standard atmospheric pressure. But anyone who has made authentic paella knows this prediction is spectacularly wrong. At the bottom of the pan, something magical happens. We get the socarrat. The socarrat is a thin layer of crispy, caramelized rice at the very bottom. It's golden brown, crunchy, and delicious. But according to our thermodynamic prediction, this shouldn't exist. Let me state the paradox clearly. How can the bottom layer of rice reach temperatures high enough for Maillard reactions and caramelization when there's water present that should keep everything at 100 degrees Celsius? Here's the central question. Why doesn't the presence of water keep all the rice at the boiling point temperature? The answer lies in understanding phase transitions and how they create thermal boundaries. This is where the physics gets truly interesting. As the paella cooks, water evaporates from the top surface. This is crucial. Let me write the equation for evaporative heat loss. The heat removed by evaporation equals the mass flow rate of evaporating water times the latent heat of vaporization. The latent heat of vaporization for water is 2,260 kilojoules per kilogram at 100 degrees Celsius. This is enormous. Water carries away massive amounts of heat as it evaporates. As water evaporates, something critical happens. The upper layers of rice lose their liquid water and become surrounded by steam and air. Look at what happens. Above a certain level, we have mostly steam and dry rice. This acts as an insulating layer. Below, we still have liquid water. A phase boundary forms. Let's look at the thermal conductivity of different phases. This is key to understanding the paradox. The thermal conductivity of liquid water is about 0.6 watts per meter Kelvin. But the thermal conductivity of steam is only 0.025 watts per meter Kelvin. That's 24 times lower. This is crucial. Steam is a thermal insulator compared to liquid water. The upper dry layer prevents heat from escaping efficiently. Now here's where the magic happens. Eventually, even the bottom layer loses its liquid water. Once the liquid is gone, everything changes. Without liquid water at the bottom, there's no phase equilibrium to buffer the temperature at 100 degrees. The temperature can now rise far beyond the boiling point. The bottom temperature can exceed 100 degrees Celsius once no liquid is present to absorb latent heat. Let's look at actual measurements from paella cooking experiments. These numbers are eye-opening. The bulk temperature of the rice with water remains at approximately 100 degrees Celsius throughout most of the cooking. But measurements at the pan bottom, once the liquid has evaporated, show temperatures between 140 and 180 degrees Celsius. That's a temperature difference of 40 to 80 degrees Celsius between the bottom and the bulk. This is enormous and completely violates the equilibrium assumption. Why is this high temperature important? Because it enables the Maillard reaction and caramelization, which create the socarrat. The Maillard reaction, which creates the complex flavors and brown color, requires temperatures above 140 degrees Celsius. Caramelization of sugars requires even higher temperatures, above 150 degrees Celsius. These reactions simply cannot occur at the boiling point of water. You need the dry, hot conditions at the pan bottom. Let's do a rigorous heat flux analysis to understand the energy flow. This will make the physics crystal clear. Heat flux equals negative thermal conductivity times the temperature gradient. This is Fourier's law of heat conduction. In the region with liquid water, thermal conductivity is high and convection occurs. The temperature gradient is small because heat moves efficiently. But in the dry upper region, thermal conductivity is much lower. To maintain the same heat flux, the temperature gradient must be much larger. For equal heat flux through both regions, the ratio of conductivities must equal the inverse ratio of temperature gradients. Let me give you a numerical estimate to make this concrete. Let's calculate actual numbers. Let's assume the pan bottom reaches 170 degrees Celsius, while the top surface is at 100 degrees. Assume the total depth of rice in the pan is 5 centimeters. Let's say 3 centimeters is the dry upper layer, and 2 centimeters is the wet lower layer before it dries. We can calculate the temperature at the boundary between wet and dry regions using heat flux continuity. Heat flux through the dry layer equals heat flux through the wet layer at steady state. Substituting our values, 0.025 times T boundary minus 100 over 0.03 equals 0.6 times 170 minus T boundary over 0.02. Solving this equation gives us a boundary temperature of approximately 105 degrees Celsius, just slightly above boiling. This calculation explains why most of the rice stays very close to 100 degrees, while only the bottom layer gets extremely hot. Let's understand the energy budget. Where does all the heat go during cooking? The total heat input equals sensible heat to raise temperature plus latent heat for evaporation plus heat losses. Here's the surprising part. Most of the energy input goes into evaporating water, not into raising the temperature. The heat needed to evaporate water equals the mass of water times the latent heat of vaporization. If you have 500 grams of water, you need 1130 kilojoules to completely evaporate it at 100 degrees. In contrast, the sensible heat to raise rice temperature is mass times specific heat times temperature change. For 500 grams of rice heated from 30 to 100 degrees, this is only about 70 kilojoules, far less than evaporation. The phase change boundary acts like a thermal switch. This is a profound concept in thermodynamics. Above the phase boundary, where liquid water exists, temperature is buffered at approximately 100 degrees by the equilibrium between liquid and vapor. Below the boundary, once liquid water is gone, temperature can rise freely without being clamped by phase equilibrium. The vapor pressure equals atmospheric pressure implies temperature equals 100 degrees Celsius for water at standard conditions. This is the Clausius-Clapeyron relation governing phase equilibrium. Once you remove the liquid phase, this constraint disappears. You might ask, why doesn't the hot steam from below transfer heat efficiently to the upper layers and equalize the temperature? The answer is that convection is severely limited in a tightly packed bed of rice grains. The rice acts as a porous medium that restricts fluid flow. The rice grains create tortuous pathways that greatly reduce convective heat transfer. Heat must flow primarily by conduction through the solid grains and interstitial steam. The effective thermal conductivity is a weighted average based on the volume fraction phi of solid grains versus interstitial space. This porosity effect is why the upper dry layer acts as such an effective insulator, despite being filled with hot steam. Now let's put everything together and resolve the paradox completely. Initially, when liquid water is present throughout, equilibrium thermodynamics is correct. Everything is at approximately 100 degrees Celsius. As water evaporates, a phase boundary forms and moves progressively downward through the rice bed, creating the insulating upper layer. In the final state, the bottom layer dries completely and thermally decouples from the bulk. It can now reach temperatures far exceeding 100 degrees. This diagram shows the complete thermal structure. Notice how temperature is clamped in the wet layer, but rises dramatically in the dried bottom layer. The paradox is resolved by recognizing that paella cooking creates distinct non-equilibrium thermal zones separated by phase boundaries. This isn't just about cooking. The principles here apply broadly across science and engineering. In chemical engineering, drying processes exhibit exactly this behavior. Product quality depends on managing these phase change boundaries. In wildfires, the same physics explains how soil temperatures can spike dramatically once surface moisture evaporates, affecting seed survival. On planetary scales, phase change boundaries between ice, liquid, and vapor create thermal decoupling that shapes climate patterns. In thermal management systems, understanding phase change heat transfer is critical for designing efficient heat pipes and cooling systems. The fundamental lesson here is profound. Phase transitions can break thermal equilibrium assumptions. Classical equilibrium thermodynamics implicitly assumes you're dealing with a single phase. When you have phase boundaries, new physics emerges. Phase boundaries create discontinuous jumps in thermal properties, which can lead to large temperature gradients and thermal decoupling. When phase boundaries move over time, as in Paella, the problem becomes even more complex, requiring non-equilibrium thermodynamics. Mathematically, problems with moving phase boundaries are called Stefan problems, named after the physicist Joseph Stefan. The Stefan condition states that the velocity of the phase boundary times density times latent heat equals the heat flux gradient at the boundary. This equation couples the heat diffusion equation with the motion of the phase boundary itself, creating a moving boundary problem. Stefan problems are notoriously difficult because the domain itself changes with time. Analytical solutions exist only for simple geometries. Let's return to practical cooking. What does all this physics teach us about making better paella? Control the heat input rate. Too fast and you burn the bottom before the top cooks. Too slow and you never develop the socarrat. Experienced paella cooks learn to monitor the phase boundary by listening for changes in the bubbling sound as water evaporates. Rice layer thickness matters. Too thick and the insulating effect is too strong. Traditional paella uses relatively thin layers, 3 to 5 centimeters. The final high heat burst to create socarrat must be timed precisely, applied only after most water has evaporated but before burning occurs. Modern experimental techniques have validated this theoretical picture with precision measurements. Researchers have used arrays of thermocouples embedded at different depths to directly measure the temperature profile during paella cooking. Infrared cameras can image the surface temperature distribution in real time, showing the spatial variation of heating. Temperature as a function of position and time is measured at multiple points, revealing the dynamics of the drying front. Results consistently show temperature gradients of 70 to 80 degrees Celsius across just 4 centimeters of depth in the final cooking stage. Let me summarize the key physics principles that resolve the paella paradox. First, latent heat of vaporization dominates the energy budget. Most heat goes into evaporating water, not raising temperature. Second, phase change boundaries create thermal barriers with dramatically different heat transfer properties on each side. Third, once a region dries completely, it thermally decouples from the phase equilibrium constraint and can superheat. Fourth, porous media like packed rice beds suppress convection, forcing heat transfer by conduction through pore conductors. Fifth, moving phase boundaries introduce non-equilibrium dynamics that violate equilibrium thermodynamic assumptions. There's something deeply beautiful about this paradox. It shows how everyday phenomena can challenge our theoretical understanding. A simple culinary observation that the bottom of paella is crispy contradicts a powerful and generally correct theoretical framework. Resolving it requires careful analysis of the assumptions underlying equilibrium thermodynamics and recognition of when they break down. The answer enriches both our theoretical understanding of non-equilibrium thermodynamics and our practical ability to control cooking processes. The paella paradox teaches us when and why equilibrium thermodynamics fails. Equilibrium thermodynamics is a powerful framework, but it has limits. It breaks down when phase boundaries create thermal decoupling. Phase transitions introduce qualitatively new physics that requires extending beyond simple equilibrium concepts. Careful experimental measurement reveals the subtle ways that nature violates our simplified theoretical predictions. True understanding emerges not from memorizing theory, but from confronting and resolving the contradictions between theory and observation. The paella paradox stands as a perfect case study in non-equilibrium thermodynamics, accessible through everyday experience, yet rich in sophisticated physics.